Hello everyone, my name is Tran Thi My Cam. I would like to talk about the subnano whole features of the proton membrane for fuel cells using Positron Annihilation Lifetime Spectrum. This is my grade 3 thesis at my own university. Why do I choose this topic? My research topic is fuel cell. A fuel cell is a device that uses hydrogen fuel. Hydrogen has the ability to provide energy effectively without polluting the environment. Therefore, fuel cells are expected to be a safe and efficient source. The current commercial Tran membrane is naphthalene. However, this membrane has some disadvantages, such as expensive price, limited operating temperature above 80 degrees Celsius, and permeation of hydrogen and oxygen across the membrane. This could reduce performance and battery life. The main reason is the existence of subnano hole in the structure, so we use Positron Annihilation Lifetime Spectrum, we can call PALS, to discover this. And we scale two membrane to improve the disadvantage, that is gravity ETFE membrane and ETFE PEM membrane. So we will study on PALS spectrum of naphthalene, gravity ETFE, and ETFE PEM to find out distribution and sign of the whole structure, so we can control gas permeability across membranes. The test content includes 4 parts. The first, selecting a spectrum analysis program. 2. PILS spectrum of naphthalene 212. 3. PASL spectrum of gravity ETFE and ETFE PEM. And the last 4 conclusions. So we go into part 1 together. 1. Selecting a spectrum analysis program. We place theoretical spectrum prediction models to analyze. A lifetime spectrum is a sum of several components. Each of the components is an exponential decay curve, the simple component and the complex component. So we will select 2 programs corresponding to these 2 assumptions. First, LT polymer program based on the simple component, in which F is fraction of the component and T is lifetime. You can see it the vertical axis and this is the horizontal axis. And second, MELT program is based on the complex component. 2. PALS spectrum of naphthalene 212. Current articles are analyzing the naphthalene membrane into 3 components, so we do the same analysis to see whether my data is reliable or not. So the table 1T and I value of naphthalene 212 in the vacuum when analysis 3 components, and table 2 compare the lifetime 3 and intensity value of the naphthalene 212 sample with previous reports. Based on the result, T and I are close to the previous articles, then measurement and analysis equipment system in this thesis is reliable. Figure 3, naphthalene structure. Naphthalene structure has backbone, side chains, and ionic group. Naphthalene is a semi-crystalline material. including crystalline region and amorphous region, so whole structure has different size in each phase. Because the structure had two phases, therefore analysis the three components will lose of structural information. So we propose a four-component analysis. T1 represents annihilation of p positron. T2 represents annihilation of free positron. T3 represents annihilation of all positron in crystalline region, and T4 represents annihilation of all positron in amorphous region. The table 3 T and I value of nephium 212 in vacuum for component analysis. And you can see the fitting consistent is better than when analyzing three components. So analyzing four components demonstrates good conformity when fitting into four components. Figure 4 distribution of hole radius R3 and V3A and R4 and V4P of nephium 212 when analysis for component with two programs LT and MELT. R3 represents the hole in crystalline region and R4 represents the hole in amorphous region. You can see the radius R3 is about 0.2 nanometer and radius 4 is about 0.4 nanometer and the volume V3 is about 0.06 and volume 4 is about 0.2. We continuously go into part 3, PALS spectrum of grafted ETFE and ETFE PEM. This includes three parts. 1. Grafted ETFE and ETFE PEM membrane through hole distribution. 3. Tau Arab spherical hole size. Whether grafted ETFE and ETFE PEM materials come from, the original ETFE sample is radiated and placed in a styrene solution to co-radiation grafted reactant. The resulting product is called grafted ETFE membrane. Then the grafted membrane is soaked in a chlorosulfonate acid solution till sulfonation reaction occurs. The sample obtained after the reaction is ETFE PEM. Figure 5. Lifetime A and annihilation intensity P of grafted ETFE membrane. This is the degree grafted. Figure 6. Lifetime A and annihilation intensity P of ETFE PEM membrane. Figure 7. Hole radius distribution in crystalline A and in amorphous region B. And Figure 8. Hole volume distribution in crystalline A and in a amorphous region B. You can see there is a shift towards smaller radius compared to original ETFE. Table 5. Hole radius according to Tau-Arab spherical model. On the anti-gravity degree R3 and R4 of gravity ETFE are insignificantly larger than R4 and R3 of ETFE PEM. And the subnanometer size whole structure of ETFE PEM is mainly formed by the gravity process and is less affected by the sulfonation process. So this is an important result never published before at the subnanometer dimension. Table 6. Hole volume according to Tau-Arab spherical model. On the entire gravity degree, V4 is 3 to 5, larger than V3, so the permeation hydrogen and oxygen gases across the membrane is mainly as V4. And for ETFE PEM, as gravity degree higher than 79%, V3 and V4 decrease softly and are always smaller than naphthalene, especially reduction compared to naphthalene. V3 is about 40% and V4 is about 37%, so it's reduced gas permeability and we get better chemical stability than naphthalene. And the last conclusion. First, PALS spectroscopy for whole size in nanometer and subnanometers. Second, naphthalene analysis of 4 components show a good fitting with the multi-phase and multi-scale structure, in which T3 component represent to annihilation in the crystalline region, and T4 component represent to annihilation in the amorphous region. Third, with the Tau-Arab spherical model, the nano-size whole structure in ETFE PEM is formed and influenced mainly by the gravity process. V4 is 3 to 5 times larger than V3, so the permeation of hydrogen and oxygen gas through the membrane is mainly in the amorphous region. As the gravity discrete value increases, the whole volume decreases and reduces gas permeability through the membrane. And ETFE PEM proton transmembrane as gravity degree greater than 79% has better chemical stability than naphthalene membrane. So there is great potential for ETFE and PEM membrane to be used as the proton exchange membrane for fuel cells. This is some references. Thank you for listening.